Hello everyone. So I am really first of all I'm really sorry about the message that happened in the last session. I recorded the entire session without the audio. This time it won't be happening. So yeah, let's get started. So today we'll be doing canaries and it's pretty simple really. So if you all remember, we had the stack frame above which we had the saved RBP, above which we had the return address. Now, RBP isn't really that important. If they overflow RBP, I don't think there's much they can accomplish. Of course, it's not desirable, but at the end of the day, it's not something that can hurt you. I mean, RBP points to this, and this contains old RBP, just like we've done so far. Similarly, this is the problem. Old RIP, and above that are arguments R1 and so on. So old RIP is the biggest problem because if you can overflow till RIP, you can do whatever, because once you overflow RIP with a very malicious address, you can gain control. We will come to how we can make it do things that are not there in the binary, like let's say the win function isn't there as we had it in the last video. Maybe it's not there this time. So in that case, what do we do? So for that, we have a very common protection. Now, what's the problem here, first of all? You have the buffer somewhere, right? It could be at the top, it could be in between, it could be the last the thing in the entire stack frame. In any case, we have the buffer, we start filling it byte by byte upwards, and then we basically, since there's no check, we keep writing upwards to here. That's the problem, right? That's the entire problem in case of an overflow. Now there is no mechanic. Now if you start doing a bounds check, it might be problematic because first of all the buffer size can be determined at runtime because C supports variable length arrays. Even then, let's say we are finally dealing with assembly, so any language could be having variable length arrays or some other mechanism through which they have stack based overflows or something. So C is not the point here. The point here is that we overflow. So runtime checks will be not possible. Even if they are possible, they will be very, very, very expensive because at each byte you have to check where the buffer is going. So yeah, that's there. So the other thing is just detect if it has overflowed, and if it has, then exit before you redirect to old RIP. So what you do is, you remember how everything was in the stack frame was tries to be 16 byte aligned. So what we do is we add a dummy 8 byte value uh, and it is called a canary. So what we do is when we load the binary, the kernel places special random values in memory, and using that, the assembly instructions first load those values into the stack. Then the assembly, then right before you return, there is a stack check fail function. So before you return, so okay, not in the stack, in the instructions before leave and ret, you have a conditional check that basically checks. So we load the original value that is written at a place where it's not modified. We'll come to that. and the second place is this stack variable. So we basically compare the two values. If they are the same, that means there has been no stack. It's a reasonable assumption that there has been no stack overflow. Of course, if it was that simple, we wouldn't be having this section on canaries. We would be like, yeah, so there's canaries, now you can do nothing. Of course, it's possible to overcome canaries. In any case, the premise is that if a canary is the same, there is no stack overflow. But if the canary is not same, you just abort. So it's a static fail function. I'll show you the decompilation in Ghidra as well. And that's not a set point. That's an abort. Like it's this. It's not like a. It's not like an improper value. It's like exit with a custom. Actually, it's int C instruction, but like you get the point. So yeah, we have the code. I'll show you. So we have an 8-byte buffer. We have printf, then scanf, then printf, then scanf. There's a very good reason why I have put it this way. First of all, I'm printing the address of win. This is required for a later thing. In any case, so first of all, gcc file, yeah, it's very simple this time, no flags. gcc file.p minus o out dot slash out. That's the address of win. Okay, maybe I shouldn't. It prints the same thing. Now I can type anything with these. So see, nothing happened right now. But if I do something like stack smashing detected, so this is what happens because of canaries. So we'll explore this in Flutter's Ghidra plugin. One second. Okay, so we are at entry 0. This, so as you can see, there is an undefined var1, there is a format, and there is a canary. So what we want is canary. Now the layout is, I think, is slightly messed up, but yeah, the basic premise is this. Canary occupies the topmost, okay, um, the highest 8 bytes. So highest 8 bytes. So according to our model, where the stack grows downwards to lower memory addresses, it occupies the highest 8 bytes. So it's the first variable. Following it are the other variables. There might be padding. We don't care about that. In any case, you can see. So it's printf, scanf, then var1 is equal to 0. That's the return value, all right. So I think this is not needed as such. It's just a register. It's the decompilation that caused this. So the best part about this thing is this just never returns. It's a fail function. Like it's an abort. So if I set up a, I'll show it to you in GDB. I'll set up a breakpoint at this ret, and when we crash the binary, we'll never hit that breakpoint. So yeah, there's a reason I have put printf scanf over here. And we'll come to that, and we'll also come to what this in ff offset is. So yeah, this is the basic thing. So this check is what is inserted by the compiler. You can of course write your own canaries as well, but that's kind of defeating the purpose of it all. Yep, let's see it in GDB. Once again, I'm using Jeff or Jeff or whatever you want to call it. It's not relevant. So as you can see, this this is the regular push RBP move and sub. This is the stack frame business, and this is the canary. So this is some special syntax that we're seeing for the first time. For the so we'll do a little bit of history deep dive over here as well, but it's not relevant. So we'll do it a little bit later. The thing is, you see RBP here. So this is old RBP. This is where the canary will be, and this is the buffer. So yeah, canary has been loaded, and this will be random all the time. So printf, I don't care about printf right now. Scanf A B C C D. I'll type 7 characters because it has to be the null. So yeah, that has been written to the buffer. Oh, I had to set up a breakpoint at ret, right? So yeah, so I have set up a breakpoint at ret, and I once again I do not care about the printf. Scanf A B C C D. Once again, like just to show you that it has to be D, and the current axis. Yeah. So 0x is for filling the entire buffer. Oh, my bad. Yeah. This is from the printf buffer, by the way. So as you can see, this has been changed, so there has been no mess up from my side. Okay, I should have continued. So we'll run this again. A B D C C D D D D D D D D, and see, I hit that breakpoint, so I reached that thread. However, let's run it again, and I'll show you what happens if we overflow the buffer. So the canary has been written to memory, and as you can see, even if we write 8 bytes, nothing would happen because the little end of the canary is 0. So even if we overwrite it with 0, nothing would happen. So we have to write more than 8 bytes. So this is 12, and I mean, it doesn't matter whatever I type because I've already overflown the buffer and canary has been overwritten. And think about, so you can see we did not hit the breakpoint, and in fact, if we so yeah, we did not hit the second breakpoint, and the program terminated with figabot. So this led to an abort. As you can see, static fail, 45 fail, abort, waste. The backtrace is there. That this is the main part. It leads to an abort, and abort is unrecoverable. So yeah. However, yeah, nothing. So this is what happens when you fail the canary check. And just to show you what how the check is done exactly. So we first load it first load the canary from the stack into RDX and then sub it from the memory and then check if it's zero or not. That's pretty much it. There are other methods that you can draw, you can do anything. Basically checking the other thing. So it's an equality check anyhow. And it's a conditional jump obviously. So yeah. Now about the syntax. So fs colon 0x28. So if any of you notice during execution, DS, that's the data segment, ES is some segment, I don't know, FS is file segment, and GS is global segment. It's a graphic segment or global segment, I'm not entirely sure. The point is it's zero. So all of them are zero. In fact, I'm not so sure of why CS and SS are not zero. I expected them to be zero as well. So yeah, throughout the program, they are always zero. So the thing is, they are segment registers. So now the little bit of history deep dive into what this thing is. I'll do it here. So we go back to Intel 8086, which was a 16-bit processor. Now the fun part about this was, so how do we deal with addresses? If we have 32-bit architecture, we have 32-bit registers. Similarly, if we have 64-bit architecture, we have 64-bit registers. So the neat part about this is the architecture determines the pointer size effectively, and the register determines the size of the largest variable you can hold, largest value, more like. So a pointer can fit in a single register, and this is by design and by realizing the stupidity of 8086. Okay, no offense to anyone who was there at Intel and worked on this, but like yeah, it was pretty stupid. So Intel had 20 bits of addressable space. So you can have addresses of up to 20 addresses of up to 20 bits. So 2 to the power 20 bytes were supported in memory. But since the register had only 16 bits, there was a deficit of 4 bits. Where do you get these 4 bits from? Enter segment register. So you have code segment, stack segment, data segment, file segment, global segment. ES is something I am not aware of. So in any case, so these work with in conjunction with the other registers. This is well, it's done in offset with I don't know how you refer to that. So nowadays the data is right next to the instruction. At least GOT is, and other data is well randomized. File segment, yeah, this hooked into the global descriptor table of the operating system. And GS, I have no idea what this is. In any case, so I'll just take these two as an example because that would make me simpler. So what you did was to get 20 bytes of addressable space. For those of you who are not aware with the syntax, this is just a 4-bit shift. So you have 0x01 and then you shift it to the right 4 times, 0x 1 1 2 3 4. Yeah, so it's basically equivalent to multiplying with 2. Okay, not x, x, my bad. 0b01, then this becomes 0b. So shift from 4 is equivalent to multiplying with 2 to the power of 4. And as it's obvious, in binary, if we clear the last 4 bits to 0, overflows might happen, but like it's supposed to be the job of the programmer to make sure that overflows don't happen. I IP is the instruction pointer. So using this, you get 20 bits of addressable space. Now, why is it not 32? I have no idea. Uh, yeah, so that's how Intel was designed. But like, yeah, it would have been very good if it was 32. So now we go back, go to our thing. We had file system colon 0x28, right? So it basically means it's a segment register. Now every segment register had two things actually, a base and a bound. This was dealt earlier in our early architectures. This was dealt with in MMU, the memory management unit. It stored all of these things, and these were exposed as registers to the in the ABI. So when we do this, what we basically do is base of FP plus 0x28, and then we also do a check simultaneously if it's within bounds or not. Like this also carried some sort of direction. Now this is heavily architecture specific, but there are architectures that did this. So using these, this was what was actually checked. So a little bit of dive in it. Nowadays, all these registers are just 0. I have no idea why this register wasn't 0. It should have been. So yeah. So right now, what we basically do is we read the value from 0x to 8 since fs is 0. Now, this value is suspiciously close to this, and this value, as we all know, the famous null from C programming. So to and since we also kind of know that null is something where we cannot write, this will come up later in later sessions, but memory is usually divided into something called pages nowadays. Segments was the other half of pages. Like people use segments and then they switch to pages, and some systems use segments and pages. In any case, so yeah, this entire page is marked read only by the operating system. The operating system can manage pages and it can mark pages as read only, read write, no read at all also. So this was just read only. So, oh no, sorry, my bad. It wasn't even read only because you can't dereference a null. So this, and usually a page size is like what, 1024 bytes. Usually in Linux nowadays. This is obviously tweakable. I'm not so sure how tweakable, but like it is definitely tweakable in the operating system. So this entire place and this address is obviously within this page. So the kernel loads a random value over here, and like if you have multiple canaries, you can have multiple offsets. 0x to it might is not necessary. So the kernel loads a random value over here when it's loading the binary. Once it has done loading it is done loading the binary. After that, it hands over the control to the interp, to the program specified in interp, which might be nothing. In which case it just looks for underscore start. So yeah, So elves have a complicated startup method. We will cover that in a later session. Right now, yeah, so this is basically something, the value, there's a random written value over here by the operating system, and okay, it must be read only. I think null has different semantics. Oh, no, no, you can read null, right? Can you? Not so sure. But in any case, this is read only and this is a random value. Uh, and once we access this, this will be our canary. So you can have a bunch of canaries over here. So that's how canaries work in the operating system and the binary. We want to exploit it now. So how do we do that? It's very simple. We read the canary and then we input it again. So how can you do that? Enter format string vulnerability. The biggest and the most powerful vulnerability in C probably. So if you all remember, printf takes a character array as its first argument, which is the format string, and it's a variadic function, so it can take multiple arguments. These will be set up by in assembly. That's not relevant. The point is, it has no way of determining if the thing is from, well, a hard code, if the thing is hard coded or it's like something from the stack. So nothing stopping us from having it on the stack because of ABI reasons. Printf is that way. So this is one very common mistake that people do. If they want to print buffer, they should instead write this. However, if you have, you know, some arguments for 12, 12, 12, but in that case, you shouldn't use a stack-based buffer. Why? Because scanf. You can overflow into a buffer and then you can change the format specifiers, which will be interpreted at runtime and not compile time. Mind you, they will be interpreted at runtime and they can give you arbitrary values. Don't believe me? Let's see. So %p underscore foo p percent to $p underscore foo will come to the syntax. Okay, that didn't print anything. But %p underscore foo, you see, uh, see, it prints values, and if you think about it, these are values from the stack. Why will come to, so they might not be necessarily from the stack, but like they are arguments to printf. So you see, this is man printf describes the format of format string, and this dollar. $m instead of percent, and star $m instead of star. So yeah, this will take the second argument and this will take the first argument. Now the thing is, 64 bits, the ABI is such that some of these might be in registers. It's hard to determine and it's hard to remember also which ones. At least I don't. The point is that it's not relevant which ones are on the register. What's relevant is what's on the stack. So we need to print the format, right? Let printf do it. Then scanf percent. Okay, I have done this before, so I know. Uh, so if you notice carefully, this is exactly 8 bytes, 7 bytes, and that's because I want to fit it in the buffer. I don't want to overflow the canary. So we'll continue till the next scanf, which is when we will have our thing. Now you see it printed three dots, which was our format string terminator, and this. Do you see this? So the way printf ABI works is only some arguments can be given through the registers. Other arguments are loaded through the stack. So you will have multiple arguments. So if you have multiple arguments, some of them are bound to be on the stack. So if you make printf think that you are trying to read arguments from the stack, it will read things from the stack and assume that they are arguments. That's the gist of it. I will give you a proper explanation in the next session. So this is six. This is percent. This is six. This is dollar. This is p, I guess. Yeah, this is dot dot dot. So if percent, I just filled it with a because yeah, who the hell cares? Uh, if six gives you this very naturally, so I'll tell you what the assumption is. Most of its arguments are 8 bytes. For I'm not sure how integers come into play because they are 4 bytes, but I am assuming they would probably be padded to 8 bytes or it would make adjustments. In any case, percent $6 will read this for 8 byte thing in particular. These 8 bytes. So if we use %7, that $7 that should mean it will read this value, and that's a very good thing because if we read this value, that's a canary. We can read this value, process it, and then when overflowing the buffer, we can write this in place of the canary and continue execution. For that matter, why stop here? Why not read RBP as well? So yeah, that might cause problems because that would be two two 4 characters chunks, so that would be 8 bytes. So that might overflow the buffer in some cases. I'm not sure if canary is always supposed to end with a 0. Let us assume that it does for the time being. In that case, it would be okay, but if it doesn't, then we're kind of screwed. So yeah, once again coming back to printf. So let's say we give printf a bunch of arguments. I'll show you. Let's see how many these are. One, 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 one. Okay, one, three more. Yeah, I think these should cover all the registers. Yep. Yeah, so I think we can clearly see. So first of all, for in case of printf, RDI carries the format string. That is something that's very obvious. First argument is in RSI, so they moved it to ESI for smaller instruction encoding. Then EDX, as we see EDX, ECX, R8D, R9D. I think R8D and R9D are just smaller encodings of R8 and R9, like 32-bit with encoding. So yeah, finally we call printf. So we have one, two, three, four, five. Five arguments, 1 to 5 in registers, arguments 6, 7, 8 in the stack, and well, yeah, arguments, the format string in RDI, and RAX has to be 0 every, or maybe they did it for tagging the instruction set. In any case, uh, five arguments through registers. So that's it, I would say. Yep. Might as well just run it. Yep. So in the lecture that I took that I did not record properly, somebody asked why six. That's because the first 5 hours in the register. So yeah, I think this should suffice, and we'll see an exploit using format strings in detail in the next session. For the time being, the main thing is you would want to see where the format string is exactly on the stack. That could be anywhere from 6 to higher, depending on what happens in between. I have no idea. Printf is a pretty deep function. So yeah, you would want to check what's happening and then find the format string on the stack, and in reference to the format string you find everything else that you want to manipulate. Also, just as a teaser, format string can also modify values anywhere if it's given the right pointer. We'll come to that. Not today. So that's it. And